Okay, so this mini lecture is going to look at an example of how you calculate torque acting on an object. So we've talked about what torque is. We've talked about the beginnings of a process to analyze torque using an extended free body diagram and how we make one of those. And so this lecture is going to use that idea of torque, use the extended free body diagram to actually calculate the torque acting on an object. And we're going to use our wrench example again for two reasons. One, we're going to use sort of the process we've outlined. And then I'm going to talk to you about two different ways that you can calculate torque based on that process. All right, so we have an example. Luis uses a 20 centimeter, so 0.2 meter long wrench to turn a nut. The wrench handle is tilted 30 degrees above horizontal, and Luis pulls straight down on the end with a force of 100 newtons. How much torque does Luis exert on the nut? So we're really just interested in the torque that Luis is exerting on that nut. So we want to identify our object that we are going to be analyzing the motion of. Now the nut is attached to that wrench. They're kind of rotating as one unit. And so we are going to think about that object as being that nut wrench device together. And so if we were sort of to draw a picture of that, there's sort of our bolt, I guess. I'm not very good in terms of art. So there's our wrench. We know that that wrench is 0.2 meters, 20 centimeters. And we know that Luis is exerting a force straight down, the force by Luis on the end of that wrench, and that wrench is angled at, let me double check that, 30 degrees. 30 degrees. All right, so there is our situation. Okay, I need a calculator. Pull one over. All right. So when we are wanting to analyze the torque, we need to do that extended free body diagram. So let's make that extended free body diagram on our object, the wrench. And again, I like to draw that picture in orientation of the object. So instead of a dot being that nut wrench system, we actually now have the wrench. So there it is. Doesn't look a whole lot different than my picture. We then need to draw the forces acting on that wrench. And in our example here, if we imagine this sort of in a horizontal, we're only interested in this torque. So we're just going to draw that force acting on the wrench. So there's our extended free body diagram. The rest of it's maybe in and out of the plane. This is not part of that torque around. If we think of this wrench as sort of on a flat surface, let's use that as our example. Okay, so we need to analyze the torque that's being exerted by that force. We want to keep in mind that torque, remember, is the force times the radius that force is acting times the sine of the angle, where that angle is between the force and the radius. All right? That's how you were introduced to it when we drew the extended free body diagram. So we have to identify a radius, which of course means we have to identify a pivot point. So after our free body diagram, we certainly want to make sure to identify a pivot point. A lot of different strategies for identifying a pivot point, as we'll look as we do more and more equilibrium analysis in the next sort of couple of videos and some of your homework. I'm going to choose the pivot point at the natural rotation in this case. That's a good strategy to start. Not always the strategy you'll use, but it's not a bad one. So we'll start there as that being the pivot point. Once we have the pivot point, then we can identify some of these things. So this is our radius from the pivot point to the force. That's the radius of Luis that we're interested in. And then we need to, of course, identify that angle. So we extend that pivot point. And I'm using my right hand. I know it looks like you're my left hand. We extend that radius, curl to the force. So that's the angle that we're dealing with in terms of Luis. All right, so let's calculate the torque. So the torque of Luis is simply the force of Luis times the radius of Luis times the sine of the angle for Luis. My force of Luis says that she's pulling down with 100 newtons. The radius, we are told, of that wrench is 0.2 meters. That is equivalent to the radius that we've identified from the pivot point to the force. So that's 0.2. times the sine of the angle. So what is our angle in this situation? All right, well, it's this whole angle. And we know that this wrench is at 30 degrees. And if we think about some of our geometry principles, that makes this 30 degrees. So those angles are identical. And then that's 90 degrees, because we know that from the horizontal, she's pulling straight down. So 90 plus 30 is 120 degrees. And that angle, remember, is from the radius to the force, so it is a negative 120 degrees. Now, if we utilize that angle of negative 100, if we pay attention to going from that extended radius to the force and use the direction, our direction should come out in the torque. If we don't, if we just say, well, that's 120 degrees, then we have to be attentive to the direction of the torque. So we should be able to predict the direction of the torque, positive or negative. This force is going to rotate that wrench in the clockwise direction. So we expect that torque to be negative. So let's see if that indeed works out. So the sine of 120 degrees, get to my calculator. So we have 120 negative sine of that times 100 times 0.2, and we get a torque of negative 11.6. What is our unit for torque? Well, the force is in newtons, the radius is in meters, and our unit for torque is indeed the Newton meter. So that negative is what we expect is going in the downward direction. Okay, so that is how we have looked at analyzing torque. So the torque that Lewis, I forgot what I said at the beginning now, is exerting on that wrench is a negative 11.6 Newton meters. Now we've used the idea that we use the force times the radius times the sine of the angle between the two. There is another way to be thinking about the torque. And that is, and I just want to introduce it, it is not a way that I will model very often, but you might learn it, especially if you're in a program that then is going to continue to take courses and look at torques, and it's called the lever arm. So the torque can also be examined by looking at what we call the lever arm times the force. So I'm just going to outline that method for you once. And if that's your more comfortable method and you want to talk about it a little bit more, we certainly can do that on an individual basis. The extended body diagram process, that is all the same. So I'm just going to redraw that free body diagram, extended free body diagram for us here. There's the force by Lewis. And we do indeed still have a pivot point. So there's our pivot point. Now, this L is what we call the lever arm. It is the distance from the pivot point to what we call the line of action. And the line of action is the line that falls along the force. So as if the force was acting along a single line. Okay, that sort of makes some sense, the line of action. And so our lever arm becomes this distance. It's going to make a perpendicular intersection with that line of action. So the shortest distance between the pivot point and the line of action. Now if I'm going to calculate the torque based on that, I have the force times the distance L. Well, my force is the same. Okay? So it's the same as in the previous situation. But what is my distance L? All right. Well, we know that this is 30 degrees, which makes this angle 60 degrees. Okay? And the reason I'm using that 60-degree angle is because I want you to recognize that that 60-degree angle is opposite the side L. So my length opposite the angle gives me my length L. So remember, this is still 0.2. So if I wanted to know what L was, and I was using the opposite angle, I would have the sine of the angle is equal to the opposite over the hypotenuse. And I want the opposite. So the sine of 60 is equal to the opposite L over the hypotenuse 0.2, which gives me 0.2 sine of 60 is equal to L. Now I can substitute that in here, 0.2 times the sine of 60 degrees. And what I want you to recognize is this. Now those don't exactly look identical, but since 60 and 120 make up 180 degrees, the sine of 120 and the sine of 60 are the same. And so we don't have the negative in here, so keep that in mind. But this is equivalent to this. And so the process, the method is the same. It's what we're taking as the angle and what we're looking at the component of. In this case, we talked about the component of the force that was perpendicular. And to get that perpendicular component, we take the sine of the angle. We talked about in that previous lecture when we first introduced torque. In this case, we're taking the component of the radius that's perpendicular to the force by using the sine function. It's identical in terms of the mathematics, but how we think about it is a little bit different. And either method is fine. We will find, of course, that this is going to give us 11.6 Newton meters if I plug it into my calculator. And then I have to be explicit. What is the direction of this torque? And we see that it's negative. So I want you to keep in mind either one of these methods is fine, and they're identical. They're identical because in this method, as we've talked about it, we're taking the component of the force that's perpendicular to the radius. In this method, we're taking the component of the radius that's perpendicular to the force. So either method is fine. This is the method I will model, the radius and the force cross product method. But if you're more comfortable with the lever arm method and you want to talk about that, we certainly can do so individually. All right, there's your example. I'll do one example problem in the homework for just calculating net torque, and then we'll also have an example on equilibrium. Good job.